The standard model for life's origin relies on the primordial soup, a fluid medium where early chemical precursors mixed freely in a chaotic environment. This hypothesis depends on accidental accumulation. It assumes that if molecules tumble and collide for a long enough duration, they will eventually happen upon the specific configurations necessary for biology. However, in a boundless liquid medium, the concentration of these reactants remains too low for sustained interaction. A single amino acid is more likely to drift into the open ocean than it is to encounter the exact partner required to form a peptide bond. Even when a fragile structure like a lipid boundary does form, the lack of a stabilizing surface leaves it vulnerable. Small-scale fluid currents or simple thermal fluctuations can instantly pull these nascent compartments apart. This dilution prevents informational sequences from achieving the proximity needed for replication. Without a way to anchor these components, any local increase in chemical complexity dissolves before it can be copied. The Gibsonian framework shifts this environment from a fluid continuum to a discrete catalytic substrate, utilizing the rigid, repeating structures of mineral lattices. These lattices act as physical bit sites on a microscopic motherboard. They trap chemical tokens in fixed positions, ensuring that reacting molecules remain in constant, close proximity. By utilizing a discrete substrate, the transition to life becomes a sequence of recursive updates. The lattice provides the necessary structure to turn random collisions into a directed chemical search. On a mineral lattice, reactions are no longer governed by the chance encounters of a fluid medium. Instead, they follow specific rules of adjacency and occupancy. This hardware operates under the full complement rule. A chemical step cannot advance or update until all local requirements are met. Every surrounding slot, representing monomers, energetic tokens, and catalytic alignment, must closely match. The full complement rule ensures that chemical complexity locks into place. This prevents the system from sliding backward into a disorganized state, allowing the lattice to secure each new level of organization. This lattice hardware supports a specific type of chemical computation known as recursive token lattice synthesis, or RTLS. RTLS processes 4 required pillars for life. First, boundary persistence, forming stable compartments. Second, metabolic throughput, utilizing energy gradients. Third, informational heredity, keeping token sequences stable. Fourth, reproductive closure, duplicating the state. Recursive laws then force these isolated sectors to merge on the discrete substrate. This recursive loop creates a system where boundary, metabolism, and information are no longer independent events, but integrated components of a single process. When these 4 pillars successfully integrate across the lattice, the system follows the protocell emergence theorem. This is the moment of W-sheaf gluing. It occurs when local functional loops cross their viability thresholds and lock into a unified state. These compatible local sections combine to form the first true protocell, a coherent global state emerging from the underlying lattice. This model suggests that the transition to life does not require the vast timescales often associated with the primordial soup. Instead, emergence occurs as a threshold-like burst. Once token conditions are met, the chemistry undergoes a phase transition from dormant to living. This provides a specific pathway for laboratory study. Researchers can construct mineral lattices with molecule-scale sites and monitor for the joint stabilization of metabolism and heredity under thermal or UV forcing. Under the Gibsonian framework, abiogenesis is the first stable global section of prebiotic chemistry. It is the result of lawful, token-weighted evolution achieving closure on a discrete substrate.